Hello class, welcome to this AP Statistics video. We're looking at lesson 3.1, Scatterplots and correlation. So let's talk about univariate and bivariate data. So univariate data, when you hear that word, you're thinking about data that only involves one variable. So it's a one variable data set, whereas bivariate data have generally involve relationships between two variables. So when we want to describe two variables or the relationship thereof, we want to look at bivariate data. Now there's a couple of things when analyzing two variables or the relationship between two variables. You want to first plot the data, look for overall patterns, departures from those patterns. You want to look for summaries of that data, so you want to add numerical summaries. When there's patterns that you see, you want to find a model that's simple in order to describe it. So let's talk about the two variables. Since we are looking at the relationship between two variables in bivariate data for this lesson, for this unit, we're going to look at the two different variables. So one of them is the response variable. Now the response variable, typically in a scientific study, we would refer to that as the dependent variable, which is the outcome of the study, the outcome variable. However, in statistics, we use the term response variable. So the response variable responds to a change in the explanatory variable. So if the explanatory variable changes, it's going to affect the response variable. And the response variable is what you measure from the outcome. Now the explanatory variable may help predict or explain changes in the response variable. Traditionally in the scientific field, we would refer to this as the independent variable. However, in statistics, we call it an explanatory variable, just so that we don't confuse that with independent and dependent in statistics. So an explanatory variable helps explain a change in the response variable. So when you affect the explanatory variable, you would expect to see a change in the response variable as a result. So for example, let's suppose researchers wanted to see the relationship between alcohol and body temperature. So in this example, alcohol is the explanatory variable because if you vary the alcohol level, you would expect that it would have an impact or explain changes on the body temperature, and not necessarily the other way around. So therefore, the body temperature is the outcome of the study, the measurable outcome. The alcohol levels are adjusted in order to help us predict or explain changes in the response variable. So hopefully that made sense. So there are some instances where the explanatory and response variables may actually be either variable, and it's not clear cut which one is the explanatory variable, but we'll look at some examples here. So let's look at the weight in carats and the price in dollars for a sample of diamonds. We want to determine, which of these is explanatory. So the first part, the explanatory variable is the weight in carats because the weight helps explain the price of the diamond. The greater the weight in carats, the greater the price in the diamonds. That makes sense, right? So the response variable is price because it responds to the change in the weight. So the weight of a diamond helps explain the price. Now for part B, we have the math SAT score, forget that typo there, I should say score, an SAT evidence-based reading and writing score for a sample of students. So in this case, either variable could be explanatory variable, either the SAT math score or the SAT reading and writing score, because each one could be used to predict the other. So here there's no clear-cut explanatory variable, so this one could be either or. All right, so hopefully that made sense. Let's look at the scatter plot. So now we want to display the relationship between the two variables. And how do we do that? We do that with a scatter plot. So the scatter plot shows the relationship between the two quantitative variables measured on the same individuals. The values of one variable appear on the horizontal axis, and then the values of the other variable are on the vertical axis. Each individual set appears as a point in the graph. And so let's talk about how to make a scatter plot. Well, first off, you have to label the axes. So you're going to have two axes, the x and the y. So this is important here. The explanatory variable goes on the x-axis. Explanatory, x. Easy to remember, right? The response variable goes on the vertical axis. If there's no clear explanatory variable, then that means either one can go on the horizontal axis. However, if there is a clear explanatory variable, it must go on the x-axis. All right, second thing is to scale the axes. So once you have the axes and you scale and you determine which one's explanatory and response, you want to scale depending on the data that you have. Then you want to plot the individual data values. So each of the data values plot as x, y, right? All right, so let's make a scatter plot. Do baseball teams that spend more money on players also win more games? Well, the table shows the payroll in millions of dollars and the number of wins for each of the 30 MLB teams during the 2016 regular season. Make a scatter plot to show the relationship between payroll and wins. Well, first off, we want to see if spending more money enables us to win more games, and therefore the response variable is the payroll, right? So we want to see if we spend more money, will we win more games? So the number of wins is the response to the payroll, right? So payroll is going to be the explanatory variable. Therefore, that's going to go on the x-axis. So first off, we have payroll on the x-axis and number of wins on the y. So we label the axes accordingly. Next, we want to scale the axes. So in this case, based on the number of wins and based on the payroll, we can go by 50s for the payroll, starting at 50, since, you know, the smallest payroll is in the 50 millions. And then the number of wins is, you know, around, you know, that much as well. But we're going to go by 10s all the way to 110. Keeping in mind that the number of wins is the highest number of wins, I believe, is 103. And then once we scale the axes, we're going to go ahead and plot the data points. So for example, if I look at Arizona Diamondbacks, we have a payroll of 103 million and the number of wins is 69. So it would be 103, close to the 100 mark. And then you'd have 69, which is close to 70. So we would have a dot right around there, and we would keep doing that. All right, so if we continue plotting those dots, we would get all of the data points from the set to plot the individual data values. So hopefully that made sense. All right, so here's our scatter plot. It gives you an idea. So the idea here is that in general, the greater the payroll, the greater the number of wins. Now, this is not true across the board, right? But in general, we do see a trend from the lower left to the upper right. And that indicates that there is some kind of trend in the data set. All right, so describing scatter plots. How do we describe them? Well, one of the ways that you can describe them is how I mentioned earlier, which is in the graph earlier, it was increasing, right, from bottom left to top right. That is known as a positive association. So two variables have a positive association when the above average values of one variable tend to accompany the above average values of the other variable, and when below average values also tend to occur together. Okay, so in this case, if this were average, then the below average values are together here. And so, like, for example, if this is the average for X, or this is let's say you have your data. Let me see if I can draw it real quick. So let's say you have your X and Y data. Let's say your X bar is around here, or yeah, let's say this is around your X bar. Okay, your average of all of your data points, and over here, this is your average of your Y values, Y bar. Well, then, if you have data point here, this is below average in the Y, or in the X, and it's below average in the Y, right? If you have a data point here, well, then this is above average in the Y, but below average in the X, right? If you have a data point here, then this is above average in the Y and above average in the X. And so the idea is, if you have a positive association, we have a bunch of data points where we have below average points occur together and above average points occur together. And therefore you have this pattern where it's going from bottom left to top right, Okay, you may have a few points that are below average on some of them, but in general, most of them are going to be above average together, or both below average together. All right, so hopefully that made sense. All right, so in this case, two variables have a negative association when the above average values of one variable tend to accompany below averages of the other variable. So in the same idea here, x bar, y bar, you have you may have a data point that's above average in the y, but below average in the x, and so those occur together. Then you might have a point here which is below average in the y, but above average in the x, and therefore they occur together. Okay, so that's what we're referring to. So hopefully that made sense. All right, so there's no association if knowing the value of one variable does not help us predict the value of the other variable. So it's just all over the place. There's no clear trend. Okay, so let's take a look at the scatter plots here. We have 3 of them. Which association will accompany each scatter plot? So on the top left, we had the payroll and the number of wins. We looked at that and we mentioned that was a positive association. Generally, the higher the payroll, the greater the number of wins, right? And so we can see that trend here. So that looks to be a positive association. Now, if we talk about it in terms of x bar, y bar might be around here, and then x bar might be around here. Well, we can see that most of the dots are either both below average together or above average together. Okay. Of course, this is just an estimation, right? So this is not the exact x bar, y bar, because I need to calculate it. Now, if you look at the one on the right, this seems to be a negative association, right? Which means that if you were to maybe say the x bar was around here, let's just estimate, and then the y bar is around here, where you can see that most data points are here and here on those quadrants. And this indicates where the first one here, the first region here, some are below average, but then paired with one that's above average. And then over here in this region too, we have the same situation occurring. Some are above average paired with below average. So this is clearly a negative association. And this is the number of wins versus the runs allowed. So for the MLB teams, if you allow your opponent to get runs, you're generally going to tend to lose, right? You're going to tend to have less wins. If you allow your opponents to have a bunch of runs and score points, you would expect that you would have a higher chance of losing, right? You would tend to lose. And therefore, we have a negative trend. We have less wins as we allow more runs. All right, so then the other scatter plot describes the amount of sleep and the height. Does sleep corresponds to the height? In this case, we wouldn't expect that sleep would, correlate with height. So if you look at the data here, it seems to be all over the place. And therefore, this is no correlation, or no association, rather. So there's no association between the two variables according to the data set. All right, so how do we describe a scatter plot? So first thing you want to do is you want to describe the direction. So is it positive, negative, or no association? Kind of like what we referred to earlier. You want to describe the form. So does it show a linear form or a nonlinear form? Is the form is linear if the overall pattern follows a straight line. If it follows like a curved pattern, then we would refer to it as nonlinear or curved or curvilinear. All right, so here we go. We have strength. You want to see how strong is the association? Yes, it may form a line, but is it a strong, tight line? Or is it just a loose, scattered line? So is it weak, moderate, or strong? An association is strong if the points don't deviate much from the form identified. It's weak if they deviate quite a bit and they're scattered quite a bit from the form. And then we have unusual features. So for example, if you have any outliers or points that fall outside of the overall pattern, maybe you have distinct clusters of points as well. You want to look for any unusual features. All right, so remember that when you're describing the association in the scatter plot, you want to talk about context. Context is key to maximize points on the FRQs. So this means that you need to use both variable name and both variable names in your description. So whatever x is, you want to describe that. You want to explain what that is. And whatever y is, you want to use the name for that as well. All right, so let's look at an example. So here we can see that if I'm describing the SAT math score and the percent of students who take the SAT for the 50 US states, if we want to describe the association, well, look, if you look at this graph, it looks to have a sort of curvy nature to it. So you can see that it kind of looks like it. The graph kind of looks like it does this. If you can, hopefully you can kind of see that. Or let me try to draw it a little better. So it has a curvilinear nature to it. So it's definitely not straight. It looks like, and it's negative, right? Because it's going down as x is going up, the y value is going down. So you can kind of see that in the graph. So we have and it looks pretty strong. It's pretty strongly tight. It's tight to that curve, so it doesn't stray much from that curve. So that's good. And it's negative, curved, and it's moderately strong. So we'll say it's moderate. And then if we look at, so we described the strength, we described the direction, we described the form, and now we want to talk about, you want to include context, right? So between the percent of students in a state, that's the in a state who take the SAT, so that's the x value, and the mean SAT math score, there's your y value. So that's the context. Unusual features. There are two distinct clusters. We can see that there's a cluster around here. There's a cluster around here. We also see that there's some points that fall outside of that. So we can see a point that falls outside of the pattern there. We see another point that falls outside of the pattern there as well. Okay. All right, so we talked about strength, direction, curve, form, and then unusual features. So those are the things you want to look for, SDFU. So strength, direction, form, unusual features. All right, so hopefully that made sense. So when the association between two quantitative variables is linear, we want to use something called the correlation coefficient, otherwise known as the correlation for short. And the symbol for that is R. So the correlation, what it does is if you have an association that's a line, remember the previous example was not a line, it was curve. It was a curve, right? But if you have something that looks like resembles a line, then you can measure the strength of that correlation by using the correlation coefficient R, right? So we'll show you how to calculate this in a second, but the R measures the direction, so whether it's positive or negative, as well as the strength, okay? So remember, it's only appropriate to use this when you're looking at linear relationships. And R is a value between 0 and 1, or between -1 and 1, sorry. Between -1 and 1. So if R is 0, you have no correlation or no linear association. If it's -1, you have a perfect negative association or a perfect negative correlation. And then 1 is a perfect positive correlation. Okay, so some important properties of the R. This is what I mentioned earlier. It's between -1 and 1. It indicates the direction. So if it's positive, then it's positive association. Negative is negative association. The extreme values occur in perfect cases. Ideally, this will not happen because the points have to be on a perfect line, right? On a perfect linear relationship in order for it to be perfectly 1 or -1, right? This will be an example of R equals 1, perfect, right? It's generally not going to occur that way, right? In the real world, there's going to be things that happen that make it deviate from perfect linear relationship. So most of the time, it might be close to 1, but not exactly 1. All right, so if the linear relationship is strong, then it will be very close to 1 or -1. If it's moderate, it's somewhat close. And then a weak, it's not very close. It's closer to 0 than it is to 1. All right. So there you go. All right, so let's look at a few scatter plots and determine what are the correlations. So if you look at the top left, it seems to, if you look at the data, it's pretty scattered. So we would expect that the R value will be quite low. In fact, it's going to be 0 because there doesn't seem to be any direction associated with these points at all, and they're scattered all over the place, right? So there doesn't seem to be a trend. Now the one in the top middle, there seems to be a loose trend, right? A loose negative trend. So we would expect that it would be a negative correlation. However, it's pretty weak. So we would expect to be maybe 0.2, 0.3. So here we go. So it's about negative 0.3. All right, so the correlation on the top right, again, it looks to be a positive correlation, although it doesn't look to be too strong, right? But you can see that some of the curves, some of the points do follow it. So in this case, the correlation is 0.5. So it's definitely stronger than the one on the left, but still not as strong as it could be. On the bottom left, we have a negative correlation. This definitely looks like it's a tighter fit to the line. You can definitely see that most of the points seem to have that structure where it's following that trend overall. In this case, it's going to be negative 0.7, so it's increasing in strength, as we can see. Definitely increasing in strength. You can definitely tell as we're proceeding. This is a positive correlation, and it's definitely increasing. It's going to be about 0.9 for this. And then finally, the last one is a negative association. Look how tight the points follow that line, negative 0.99, very close to that perfect linear relationship. All right, so hopefully that gives you an example of each of the correlations. All right, so here's the scatter plot showing the relationship between the payroll and millions of dollars and wins for the MLB teams in 2016. For these data, R is equal to 0.613. Find the value of R. Okay, so we've looked at this data before. We've said that it's a positive association. We knew that it has that linear trend. Here, they give us the R value, the correlation. So let's interpret it. So what that R tells you is the strength, and it tells you the direction. So here, we're going to say the correlation confirms we have a linear relationship between payroll number wins that is strong moderately and positive. All right, 0.6 is around moderate. Once you get to 0.8, 0.9, we would consider that pretty strong, right? So it kind of gives you an idea of what could we consider moderate versus strong for this. And then weak is going to be, 0.4, 0.3, 0.2. Those are considered weak, right? And so on and so forth. It's all right, just to give you an idea. Okay, so note about correlation. Correlation doesn't imply causation. This is important. So, for example, if we are talking about the number of shark attacks and the number of ice cream sales, you would see that there's a positive association between the number of shark attacks and the ice cream sales, right? Let's just say we have a graph that looks like that. Does this mean that the number of the ice cream sales caused the increase in the number of shark attacks? And the answer is, of course not. And vice versa, right? The number of shark attacks didn't necessarily cause an increase in ice cream sales. So correlation doesn't imply causation. Just because we see a correlative, a relationship between the two variables, doesn't mean that one necessarily caused the other. There might be another variable involved that caused it. Okay, we call that variable a confounding variable. Confounding. So, for example, here you could possibly attribute this to maybe the time of the year, maybe the temperature. As the temperature increases, depending on the time of the year, right, you might have an increase in ice cream sales as people get, hot, right? If the temperature increases, you might have people go to the beach, for instance. Increase in ice cream sales might be increased by that increase in temperature. But then also, if people are going to the beach, then it might lead to an increase in shark attacks, right? So there might be a common variable that links the two that actually is the ultimate cause of both of them increasing. So hopefully that made sense. So correlation does not imply causation. If you assume that, then you'll assume some pretty crazy, you'll draw some pretty crazy conclusions when you look at data, as for example the one I provided here. All right, so correlation doesn't imply causation. Correlation does not measure form. So just because you have the correlation, it doesn't actually tell you the form of the data, right? Because the data could be, we know that the correlation coefficient R is supposed to measure linear relationships, but that also doesn't tell you exactly how the graph looks like, right? Correlation should only be used to describe linear relationships. Okay, so again, things that look like they're approaching a line. Correlation is not a resistant measure of strength. So if we, for example, if we introduce outliers, that is going to impact the correlation. So you might have a bunch of tight points here, but then if you have a bunch of points here, so on, that's going to affect your correlation, right? Because then it's going to make the data go maybe like that, make the potential linear trend go like that, or it might make make you think it's a curve, right? So you want to be very careful. It will definitely affect your interpretation of the form, and therefore, the R as well. All right, so keep that in mind. So how do we actually calculate the R? So we talked about what R is and what it does, and that it's for linear relationships, but how do we actually calculate it? So calculating R is a bit, it's tedious. It's not necessarily difficult, but it is a tedious procedure. But we'll show you how to do it. We'll show you in a full-on example of how to do this. So suppose that we have n individuals for variables x and y. So let's say that the values for the first variable are x1, y1. Then we have the second ones are x2, y2, so on and so forth. So then what we could do is we can find the mean and the standard deviation of both variables. So we have x bar and sx. We have y bar and sy, right? For the different variables. So to calculate the correlation, we use the following two formulas. This is the formula that I'm going to use. This is their shorthand, because remember, we know that the formula for the z-score for a zx is x minus x bar over standard deviation, right? We know that that's what the formula for the z-score is. It's the individual minus the mean divided by the standard deviation, right? So that's usually what the formula is. So that's exactly what we're gonna do here, right? So we're gonna use x bar and sx. Sometimes we use mu or sigma, but remember, if we're doing this for a sample, then we want to use x bar and sx, okay? And then zy is just a y version of that. So if I change this to y, then this is going to be just a y version, right? So y minus y bar over sy. Okay, so this is basically the same formula as that. This is the same formula. So therefore, this is the shorthand. Okay, so there's a lot going on with this formula. Well, first off, you have to calculate the z-scores for each x value that you have in your data set, and the z-scores for each y value, and then you have to multiply those two z-scores together for each of the x, y values. That's a lot of work. Not only that, then you have to sum them. You have to add them together and get the total, then divide by n minus 1. All right, so there's a lot going on here that meets di. So we're going to show you how to do this. We're going to set up a nice organized table for this. Well, first things first, let's talk about the properties or things to remember about the correlation. The correlation requires that both variables be quantitative. So you can't use this with categorical variables. You have to use quantitative variables that are measurable. The correlation makes no distinction between explanatory and response variable. So you could switch x and y, and it's not going to change the result of your calculation. And you can see that because it doesn't matter if you do zx times zy or if you do zy times zx. And so in other words, if you switch y and x, it's not going to affect your calculation, right? Because multiplication is commutative. Number 3, r does not change when we change the units of measurement of x, y, or both. So remember that r is unitless. So there's no units for r. And therefore, it doesn't matter if you change the units of x, y, or whatever, because r is going to remain unitless anyways. And number 4, the correlation r has no units of measurement. It's just a number. All right, so let's show you a full-on calculation. Well, before we actually get into that, this is the problem where we will calculate the correlation. However, we're going to first describe the motivation behind that formula, right? That formula that, you know, the zx, zy formula for r. So we're going to talk about the motivation behind that. So first, you got the data here that is shown for a random sample of 6 high school seniors. We measured the foot length and measured their heights. So we wanted to see if there's a relationship between the foot length and their height. And we can kind of see from the data, there seems to be a relationship, right? A positive correlation here. So what is that correlation? We're going to calculate it. First off, what we're going to do is we're going to calculate the mean foot length and the mean height. All right, so we have 6 foot lengths. Let's calculate the average of those. So that's going to be x bar. So it doesn't matter whether you do a foot length is x or height is y, because there is no clear explanatory variable here, right? The explanatory variable could be height or it could be foot length, right? Height could explain foot length, or foot length could explain height, right? So either one could explain the other one. But here we're choosing x to be foot length and y to be height. So we're going to do our x bar. We're going to add up each of these values for the foot lengths and divide it by 6 seniors. We get 26 centimeters. All right, so we got 26 centimeters for the foot length. And then for the y bar, we're going to add up all the heights in centimeters. So we get about 168 centimeters. Now we're going to plot them. So x bar is going to be 26. Let's graph that here. So that's x bar. And that's the 26, and then we got the y bar, which is 168. Okay, so notice here we got 2 quadrants, quadrant 1, quadrant 2, quadrant 3, quadrant 4. We notice that most points are in quadrants 1 and 3. Okay, and that tells me that there is a strong there's a very good positive association here. This is definitely positive association based off of that. We only got 1 point in quadrant 4 that is off of this pattern. Okay, so those are things you want to keep in mind. Now what we're going to do next is we're going to convert the heights and the foot lengths to z-scores. So we're going to convert this to a z-score, we're going to convert this to a z-score. All right, so that's what we're going to do next. So here we go. We converted those to z-scores, the z height and z foot length. So in this case, the height of 170 is going to correspond with the height z-score of, or it was the y bar that we had here of 168 is going to correspond to a z-score of 0. All right, so so then we're going to go ahead and mark those lines right here. So this was originally the y bar, right? Originally it was that, and then originally this was if you go back to the data set here is 26. Okay, but now they're in terms of z-scores. So now this is zx is 0 and this is zy is 0. Okay. So it's the same pattern, but now it's in terms of z-scores. So now notice that most of the points that are in here and here, if you have points in quadrant 1, then these are going to be when the zx is positive and the zy is positive. So therefore, zx times zy is going to be positive, right? A positive times a positive is a positive, right? Now, if you look at quadrant 2, we have the z-score for x is negative, but the z-score for the height or y is positive. So in this case, when you multiply them, the product is negative, right? So that's telling you that any points in here will contribute to a negative correlation. Then if you go to quadrant 3, where a lot of points are, We notice that the zx is negative, but the zy is also negative. So zx times zy, a negative times a negative, is a positive. So let me put positive here. This is negative, this is positive. Therefore, points in quadrants 3 will contribute to a positive correlation. And then lastly, we got quadrant 4, so where zx is positive, but zy is negative. So if I multiply those two together, I get a negative. And that contributes to negative correlation. So you can see if the points are evenly spread between quadrants 1, 2, 3, and 4, it's going to level out. Positives and negatives are going to cancel out, and it's going to lead to a zero correlation. But if you see a lot of points in quadrants 1 and 3, it's going to lead to a positive correlation. And likewise, in quadrants 2 and 4, it's going to lead to a negative correlation. That's what we notice. So most of the dots are in the first and third quadrants, indicating the data shows a positive correlation between the two variables. So this is how this relates to this formula. It's the sum of the product of the z-scores divided by n minus 1. Okay? Okay, so now we kind of talked about that association, what that means. Now let's do a calculation. So I put the foot length. This is the foot length here. And this is the height, right, in centimeters. And I put them in these rows, right, or in these columns. Okay, so next, what we want to do, remember, the formula we want to calculate is R is equal to this sum of x minus x bar over n minus 1, y minus y bar, right? Over, sorry, I forgot to include the sx, right? So the sx, and then we have the sy, and then all over n minus 1, okay? So that's ultimately what the formula is. Let me put parentheses around these. Okay, so that means we have to calculate x bar, we have to calculate y bar, we have to calculate sx and sy. We got to calculate a lot of stuff in here, right? So let me rewrite this formula down at the bottom. Okay, so let me kind of break this down. Okay, so you might recall that to calculate the standard deviation, what we need to do is we need to do the square root of the sum of the deviations squared divided by n minus 1. So that's the formula for the standard deviation. Okay, so that means that we need to calculate x bar, we need to calculate the deviations, x minus x bar, and then we need to calculate the square of the deviations, and then we need to add them together, divide by n minus 1. So you can see why I included the deviations here, the deviations squared, because that's going to help us find our sx, and then use that information to find zx. And similarly, we're going to do that for zy. Okay, so there is the motivation behind the table. So now let's go ahead and do the calculations. All right, so let's calculate the deviations. There should be a bar here, x bar, y bar. So just make sure you include that there. It's not showing very clearly on the video. All right, so x minus x bar. We need to calculate the average. So we're going to total this column here, and we get a total of 156. This is the sum of the x's. And then we're going to do the sum of the y's. So add the y's together, we get 1008. And remember, to find the x bar, we got to add these up, divide by how many. So we take the sum, divide by how many data points, which is 6. All right, so we divide that by 6, we get 26 here. All right, and we do the same thing for y, 1008 divided by 6, 168. So now we have our x bar and our y bar. So now we're going to take our x minus our x bar to get this, all right? So we take our x, which is 23, minus our x bar of 26, and that gives us -3. So that's this data point here. Then for this point, we do 32 minus 26, and that gives us 6. And so we do repeat that for the rest of these. All right, next we're going to do the y minus y bar. So we got 167 minus 168, which is -1. So we do this minus that here, show the work here, it's -1. And then we do 188 minus 168, which is 20, and we'll repeat that here for the rest. All right, so now we're for this fifth column, we're going to take the third column and we're squaring it, right? We notice it's the same as the third column, but with a squared there. So we're going to do -3 squared is 9, right? So that's this part, -3 squared is 9, and then 6 squared is 36, and we'll repeat that process down. And we're going to take this sixth column and we're gonna take the fourth column and square it. So -1 squared is 1, 20 squared is 400, and so on and so forth. All right, so the reason why we calculated the squared deviations is because we're going to use that to calculate our standard deviation. So we need to sum the total of this column. So the sum of the squared deviations is 78. Then we're going to sum the squared deviations for y to get 1208. Then we're going to use the 78 to calculate the standard deviation for x. So it's a square root of the sum of this total, right, the 78, divided by 6 minus 1 people that were surveyed. You get 3.9. We're going to repeat this for the sy to calculate the standard deviation for y. So we're going to use 1208, divide that by 5, take the square root of that to get sy, 15.5. Okay, so this is how we got sx and sy. So now we're going to calculate zx. So to calculate zx, remember, we have to do x minus x bar divided by sx. So let's go ahead and do that. So the formula for the z-score is x minus x bar divided by sx. So we take the third column, -3, and we divide it by sx, which is 39. And we get -0.77. For the second value, we would take 6 divided by 3.9, and that will give us 1.54. And we repeat that as we go down. Now we're going to calculate the z-score for y, so zy, sub y. So we have to take the fourth column, which is y minus y bar, divided by sy. So -1 divided by 15.5. So we do that here, we get -0.06. For this number here, we have to take 20 divided by 15.5, which is 1.29, and we repeat that. Next, we're going to multiply the zx and the zy together. So we multiply these two numbers together to get 0.046, so the work is shown here. We multiply 1.54 times 1.29 to get this score, so we get 1.98. And we repeat that for the rest of the data points. All right, we're almost done. So now we can go ahead and take the sum of this last column. So we're going to do the sum of the product of z-scores, which is this column. So add those up and you get 4.273. All right, and then so now we are going to put that into the formula for R. So R, remember, is the sum of the z-scores multiplied divided by n minus 1. So the sum of the z-scores multiplied is this 4.273, put at the top, divided by 5. And we get a correlation coefficient. We get a correlation R of 0.85. All right, that's a lot of work to be able to calculate this. However, we're going to show you how to use this use a calculator for this, but I did want to show you how to do the calculation by hand. All right, so there's our solution. That's pretty strong correlation, strong positive correlation. Okay, so now we're going to go ahead and show you how to calculate the correlation coefficient. We should get approximately 0.85, 0.84 around there when we do this because we're using the calculator, and it should match up with what we did by hand. So now we're going to use the same data points. So first things first, we are going to hit stat. Then we're going to go enter. We're going to enter our data points, these data points here for x values. Then we're going to use the right arrow key for L2. We're going to hit and type in the y values for that. So type them all in. Okay. Then we're going to exit out of this. So we're going to hit second quit, or second mode. And then we're going to go to second or stat. We're going to go to calc. We're going to hit linear regression, number 4. All right, and then we're going to L1, L2, just go to calculate. All right, once we do that, we're going to go to vars. We're going to go to statistics, number 5. We're going to go to EQ for equation. We're going to go down to R, which is number 7. And then enter. And there you go, we got 0.84 for our result. Pretty close to the 0.85 that we got. Alright guys, that's going to do it for the video. I hope you found this useful and informative. As usual, I'll see you in the next one.